Hello and welcome to the physics video lecture. Once again, physics 4B. This is video lecture 25. And we're talking about electromagnetic waves. So I'll do a little bit of a review there. We obtained what I called wave equations from Maxwell's equations. And Maxwell's equations were the laws of electricity and magnetism. So in brief, it went like this. We have the laws of electricity and magnetism in integral form, and in that form, they were really generalizations of experimental results, okay, laboratory results. We then turned them into, so let's go ahead and write here, integral form. So then we turned them into differential equations. That just looked like a purely mathematical move, but it did make the assumption that these laws that we had here from laboratory style hold true in an infinitesimal region of space, okay? So with that assumption, we convert to differential equations, and those are called the Maxwell equations. So Maxwell equations. And then really we just took those differential equations and plugged one into the other, and we obtained the wave equations. So as far as converting to differential equations and then going to wave equations, we had differential operators, but that's just first and second order derivatives. That those operator identities I put up there, differentiation identities, you could just work those out by the definitions I gave. Okay, so if you have some time in the summer, just work them all out, and then there are no gaps in our discussion there. Good, so we converted differential equations, and then we obtain the following two equations. D squared E dt squared, that was a vector, equals 1 over mu naught epsilon naught del squared E. And the same thing you get for B. I didn't do it explicitly, but it's exactly the same process. So I'll say that we also found d squared B dt squared. These are partial derivatives. 1 mu naught epsilon naught del squared B. And I had given the definitions. This is just the sum of the second derivatives, divergence of gradient. So yeah, we have these equations here, and there was for the case where density is 0, current density is 0, which is to say in space, in empty space. E, empty space. So good, I've identified these as wave equations, and I'm just going to justify that a bit, or show what that's about. And we had a couple homework problems that asked us to do the same thing. So these are wave equations with the wave speed well, speed is often designated as v. For this particular speed, it gets the letter c, and that's 1 over the root of mu naught times epsilon naught. So fine, you can actually plug these two quantities in and calculate this number here, and you find that it is 3 times 10 to the 8 meters per second. So at the time Maxwell found this, this number was a known quantity. It was namely known as the speed of light. Okay, so there's the idea that these electromagnetic waves are propagating at the speed of light. Therefore, first of all, there's apparently such thing as an electromagnetic wave. Second of all, it propagates at the speed of light. Therefore, maybe light itself, visible light, is an electromagnetic phenomenon. Okay. So I think I ended the lecture with that last time, and that's just one of the greatest moments in history, but it has to be demonstrated. You know, you have to prove that. This is a theoretical development. Good. Well, let's talk a bit about wave equations. And the best thing to do is just to start with the wave equation in one dimension. In one dimension. Okay. For example, the x direction. And you know, these are vectors, so there are three components potentially of each of these quantities, electric and magnetic field. So what we have there is, we'll say we have d squared phi dt squared is equal to v squared d squared phi dx squared. Okay, so that's this del squared is the derivative in x, y, and z. I'll just put it here just to remind you guys. Del squared equals d squared dx squared plus d squared dy squared plus d squared dz squared in Cartesian coordinates. So we just have this one because we're working in one dimension only, okay? So the thing to do is consider a function we've already named it phi, say a function phi equals phi of x plus minus v times t. So phi is just a function of one variable, and so we could just graph it phi of x as a function of x. So if we do that, just give, for example, say it's like a pulse. Okay. You could construct or just name or take some function of this form. So if this is phi of x, and now I replace the argument with phi of x plus minus vt, then at t equals 0, I have this function here. At some later time, x plus minus, in fact, let's just do minus vt for the moment. X minus vt. At some later time, this point that is phi of 0 is now there when x minus vt is equal to 0. Okay, so when x is equal to v times t, which could be out here somewhere. Okay. So this is why at time t, our new function, or our function, would be out here. So if this is x equals 0, t equals 0, then over here in the red we have x equals v times t. Okay. Because x minus vt is then 0 again. Okay. So good, x equals vt, and you can see this pulse, or this function, has moved to the right with speed v. So function v of x minus vt moving to the right speed v. Okay. That's clear enough. And in fact, if I had the plus sign here, it would be moving to the left with speed v. Okay. Good. So that's the discussion of this function as a pulse moving to the right with that particular speed. Now let's apply this differential operator to this function here. So now what do we get? Now we could say d phi dt is equal to phi prime of x minus vt times negative v. Okay. And d squared phi dt squared, so I take the second derivative, and negative v is a constant. I'm going to take a second derivative here, phi double prime of x minus vt. I've got the minus v, and I bring out the minus v again. So that's minus times minus is plus, that's v squared phi double prime, which is to say that's v squared phi dx squared. I'm doing it with regards to the variable x. And what do you know? D squared phi dt squared equals v squared d squared phi dx squared. So there's our wave equation. And we can say a wave, for starters, is a function that moves here with speed v as a pulse. So that's the basic property of the wave equation. Now, what we want to go from here to sinusoidal waves that are also very common, and we can do that. Yeah, so we've got this idea here, phi is phi of x minus vt. So next let's look at the following. Phi is equal to some constant times the cosine. Now we could just write the cosine of x minus vt. Let's do it this way, cosine of kx minus omega t. This is a standard form in which we put the wave function, because if we just hold t constant, we have a cosine, a wavy function in space, okay? And if we hold x constant, then we have an oscillating function in time. And there's a relation between k and omega that'll become apparent. So let's do this. Again, I'll go ahead and write the wave equation down. Again, we have d squared phi dt squared is equal to v squared d squared phi dx squared. That's our wave equation. Let's see if this is a solution. Here, the second derivative with respect to time is going to be d squared phi dt squared. Well, the first derivative we have minus a, actually, yeah, cosine minus a sine kx minus omega t. Okay, so with respect to time, now the inner derivative is minus omega. Well, that's the first derivative. We'll do one at a time. d phi dt, d squared phi dt squared. We're going to have this minus a. Derivative of the sine is the cosine kx minus omega t. We already had the minus omega, we get another one. So that's going to be minus omega squared a cosine kx minus omega t. Good, that was the two time derivatives. Now what about the two space derivatives? Here. One. So next, b squared p squared phi dx squared is going to be equal to well, let's do one at a time again. Well, we'll do it this way. B squared d of dx. So what was the first derivative? Minus a sine kx minus omega t times k. And that is going to be v squared minus a cos kx minus omega t. Here add a k, we get another k squared. So what we're requiring now is that this star expression be equal to that double star expression. So we have to compare. We've got the minus a cos kx minus omega t minus a cos kx minus omega t. So what we're saying is apparently v squared times k squared is equal to omega squared. So it is a solution. So I already gave stars now. Let's call this star, this double star, and this triple star. Okay, so good. Star is a solution, or phi is a solution. Right. Star when, and this is the big punchline, omega squared is equal to v squared k squared, right? Or omega is equal to v times k. So that is called the angular frequency, that's the speed, and that's the wave number. So let's go ahead and graph what we have now with these sinusoidal waves. So now here's our x-axis. So at some point in time, and we'll just choose a good one, we've got a cos kx. So phi of x and t is equal to a cos kx minus omega t. We now see that omega is equal to v times k. And so what we're going to consider this thing is so let t equal 0. So now we just have cosine kx. Well, we know this function pretty well. 3, 4. A minus a. And we can repeat. So this, of course, is a periodic function, and what we can see is that when k times x goes through 2 pi, then it repeats itself. Okay, so we have k times x equals 2 pi. When x is equal to what we're going to call the wavelength lambda. Okay. So k times lambda is equal to 2 pi. So k is equal to 2 pi divided by lambda. Lambda here is called the wavelength. So lambda is the wavelength, and k is called the wave number. Now we also have periodicity in omega t here, and we're going to have the period. So we also have periodicity in time, right? So we could just let x equal 0 and ask what's happening in time, and then we're going to quickly see that omega times t is equal to 2 pi defines the period of oscillation. Period of oscillation. So it's a repeating phenomenon, and now we can go up to here and evaluate this. So we're going to have omega is equal to 2 pi divided by t on the one hand, and v times k is going to be v times 2 pi divided by lambda. So actually we have all kinds of interesting relations here now. So, which one do we want to pull out first? We're going to have defined the frequency. This is the angular frequency because we're going through, a full cycle of the cosine. The frequency we're going to define as 1 over the time period. So that's called the frequency. We use the word frequency pretty interchangeably, but omega is actually the angular frequency, and this is just the frequency here. And another relation here, let's go ahead and send this up. It follows right out of this. So then we would have 2 pi f is equal to v times 2 pi over lambda. Okay. 2 pi's cancel, and we get lambda times f is equal to v. So that's also fundamental for wave phenomena. The wavelength times the frequency is the speed. And to mention the units now, the units of lambda are going to be meters. The units of frequency are going to be inverse seconds, so 1 per second, and that's called the hertz. Okay. And then, of course, this is going to be meters per second. V is equal to meters per second. Good, so those are the basics of the wave equation, sinusoidal wave, and the relations between wave speed. We put a box around all of these, right? These are the ones that are crucial. Well, they're actually all crucial, aren't they? Lambda f equals v, that's key. frequency 1 over period. Yeah. Just for the sake of putting a red box around everything. This is actually the way I remember these. This relation here, omega p times k, omega t is equal to 2 pi, everything else follows. Everything else follows. But yeah, we have all these. Okay, good. So let's, having discussed this, I'm going to consult the clock. Okay, so much to talk about, but good. This is a nice discussion. I think our homework problems were really going over this stuff, so you should be in good shape on those homework problems. Now let's return with this knowledge back to the wave equation. I'm sorry, back to the electromagnetic wave and its equation. So, yeah, I can erase all this stuff. So back to the electromagnetic waves, which are vectors. So what we're going to do now is consider an electromagnetic wave propagating in the positive x direction. Let E equal E0, still a vector, cosine kx minus omega t. Okay. So we know what we're going to have. We know we're going to have omega is equal to c times k. And the speed of light we already had up there. Okay, that's our wave speed. Our differential equation is d squared e dt squared, the vector, is equal to c squared d squared e dx squared. And based on what we've just done, it satisfies the equation, right? We already did the work on this. This is the del squared when you only have the x direction, okay? So that's good, right? There's only an x dependence here. So let's go ahead and say this wave is propagating in x direction. So this wave propagates in x direction. And in fact, we refer to it as a plane wave. Plane wave because it takes on the same value. You know, if you were looking at x, y, z, everywhere in the YZ plane is the same value propagating to the right. Okay. Because we only have that x dependency. But we don't really know about this vector yet. Anything else before we talk about that vector? Yeah, I just want to stress again, we have this because we proved it in the one-dimensional case. Okay. Now, here's what we're going to do. Recall that divergence of E is equal to 0. That was one of our Maxwell equations for the vacuum. Okay, so that means that dEx dx plus d ey dy plus dez dz is equal to 0. Now let's inspect this. We don't have any y dependence or z dependence in this expression here. So these are trivially 0. And since the divergence is 0, we can therefore say that dex dx is equal to 0. But dex dx would be just minus k e0x sine kx minus omega t. Well, the only way that can be 0 is if e0x is 0. So therefore, and if e0x is 0, then e sub x is 0. So you can say, therefore, e sub x is 0. So what does that mean? It means that we have what's called a transverse wave. It means that the electric field vector, right, this is an electric field vector, does not have a component in the direction of travel. It has a component perpendicular to the direction of propagation. And that's what's called a transverse wave. So I'm going to draw that conclusion and then restrict myself to some generalities. Just wanted to show how these conclusions are all drawn and constructed. So this means, right, because of this, I'll just, therefore, E is a transverse wave. They've talked about waves, longitudinal and transverse waves back in Physics 4a. And transverse means, it's very nice to draw transverse waves because it means that they are perpendicular to the direction of motion. So if the wave is propagating to the right, the way we set it up, then the E vector lives in the YZ plane, and we could just restrict it to the Y, right? Z is coming out of the board, so this is our E field at a given point in time, and it is propagating to the right. Okay. So this is our E vector, and continued and similar discussions along these lines. You notice we had to go back to the Maxwell equations, allow us to show that the B field goes like this. So the B vector is in phase with E and is perpendicular to B. So here I'm just going to write, it can be shown because we don't have time to show everything. So also B is perpendicular to E and in phase. So yeah, you have these E and B fields propagating to the right at the speed of light. And so we've generated some of these. There's a whole list of other properties that you can generate as well systematically, just using the mathematical equations available. Let's see how much we're going to do. Yeah, once again, I'm going to consult the clock. Good, so those are some of the facts here. I want to mention a couple more things, and you can look this up in your text. There is the electromagnetic spectrum. Okay. Remember, we have lambda f is equal to the speed of light And we were not restricted by any wavelengths or frequencies. Okay? We had omega is equal to c times k, and as long as your frequency is related to your wavelength like this, anything's possible. So the electromagnetic spectrum is extremely wide, extreme range, and the visible light is just a very small part of it. So if you go in terms of wavelength, then you've got a very small, hey, I've got some colors here. In fact, you have your red. Here's what we'll do. We'll get rid of that blue there. Let's do this in black. Okay, so electromagnetic spectrum in terms of wavelength. Then we have a very narrow range where red is a longer and blue is a shorter wavelength, and all the colors in between there. So I'm just going to write visible, and you guys look these up. I think I'm going to assign a problem where you can get some numbers on these. Okay. Visible, and then as it gets longer here, you would have what's called infrared, and you're going to feel that as warmth. Okay, we're talking about infrared back when we were doing heat transfer by radiation. Okay, you feel this on the shorter side over here. You're going to have ultraviolet. And that'll give you a sunburn. And as you go to the shorter and shorter and shorter, higher and higher energy, more damaging radiation. And as you go longer and longer, you're going to go from infrared up into microwaves and radio waves and so forth. So once again, the visible spectrum is very, very narrow. In fact, I'll just put these numbers up. You've got on the order of 700 times 10 to the minus 9 meters, nanometers, and then the visible side here down to say 400 times 10 to the minus 9 meters. Okay. So 7 times 10 to the minus 7 meters. Okay, 4 times 10 to the minus 7 meters. So there's your electromagnetic spectrum. You guys go ahead and look that up and do a couple homework problems on that important topic. So with the Maxwell theory, electromagnetic waves, all manner of optical facts, optical phenomena were consistently explained, and you'll do that in Physics 4C. You'll talk about diffraction, polarization, etc. Could all be described with the wave theory of electromagnetic phenomena. However, actually producing electromagnetic waves and measuring them took quite a bit longer, took another couple decades, and I'm going to use that to kind of segue into the remaining material in our couple of remaining lectures. So let's say a couple things about how are these electromagnetic waves produced, right? They're out there in nature, fine, but how can you produce them? And what technology is responsible for that? So just very briefly, production of electromagnetic waves. How do you generate them? It turns out, and this is also completely describable through the whole Maxwell theory, you have to have accelerated charges. Okay, so accelerated charges. So accelerated charges produce radiation, electromagnetic radiation. So there'd be a section in your book on accelerated charges. Let's see if I want to mention any more about that. That's a whole subject in itself. Transverse gas. Okay, I'll just write. So since accelerated charges produce electromagnetic radiation, you can have an alternating voltage if you had an alternating voltage across some circuit, that would cause E fields and charges to oscillate. So alternating voltage causes charge to oscillate. Cause charge to oscillate, then it will give off these electromagnetic waves. So yeah, how do we get an alternating voltage? Okay. You know, we can imagine we have an alternating source, and we have a capacitor here, okay? And we know that capacitor charges plus Q on one side, minus Q on the other. If it's doing it alternatingly, you're getting plus and minus Q flipping back and forth, and that is an accelerated charge, as well as, you know, alternating E fields, and you're actually going to be able to give off a wave. So we still have to discuss how we can get alternating voltages and the properties of an alternating circuit. Okay. And yeah, and check your book also, you'll see something about electromagnetic radiation being produced by accelerated charges. That's going to be how I motivate that right now, because we still have quite a bit of material to cover. Although we're in good shape. The reason I jumped to chapter 30 was to make sure we did get to the electromagnetic waves, and now we can make up the rest of the material in trying to motivate, you know, how to produce them and how to receive them. So charges to oscillate, right? That produces a wave. So the question, how to receive the wave. So if you produce it, fine, but you have to actually have a receiver on this side that tells you that the wave has arrived and really is a wave. So both of these topics, how to produce it, how to receive it, require us to go into a little bit of time-dependent circuitry, and we'll spend a little time doing that. Okay, once more the clock. We'll have time to get started on that. Absolutely. Okay, so we have to return to Faraday's law and introduce, well, while we're at it, we're going to talk about motors and generators. And, you know, production of, with generators, we can talk about the production of these alternating voltages. And then some circuits as well, so we'll make it. Okay, so now we're returning to chapter 28 and Faraday's law. And I'll just sketch how that immediately gives us a generator. Okay, so returning to Faraday's law. We have this EMF, this voltage is equal to minus d magnetic flux with respect to time. So if we can get a magnetic flux to change sign periodically, then we're going to have a voltage that changes sign periodically. So the generator is going to look like this. I have to get my perspective drawing figured out. So we're going to have, let's just put a magnet with a north pole here, another one with a south pole here. This is just to motivate a uniform magnetic field. Okay, we're going to have a uniform B field. Obviously, these magnets aren't going to provide a uniform B field, but you get what I mean. If they were close enough together, right, we'd have uniform field in between. Good, so we have the uniform field, and now we need a coil of wire. So there's my perspective there. There's an axle, and actually we're going to turn a handle. We're going to turn a crank, and this thing's going to rotate, say, clockwise if we want. Okay. So we've got this frame here, it's rotating clockwise. That's just like, you know, my book here in the magnetic field rotating like this. Okay. Yeah, my picture has the handle on the other side. Okay, let's put the handle on the other side. Okay, so we're gonna turn this thing. Now we also have wire, which I'll do in red. It's actually a loop of insulated wire, and it can have more than one turn. Okay, so we've got a loop here, insulated wire. And as we turn the handle, we're turning this thing. I have one loop, we'll have end loops later on. So we're turning that, and then we're just going to attach these things to some kind of conductors and pick it up. Okay. For the moment though, just these two ends here, where I put a dot, are going to be the point across which we can measure our voltage. So forget what's downstream there. So we're turning that thing, and what do we have? We have phi is equal to area, so let's write area A times the B field, remember that's the magnetic flux, times the cosine of the angle theta. So when theta is 0, cosine of 0 is 1, and we got the full flux. When we turn it pi over 2, it's, you know, it's in this direction, there's no flux at all. Okay. So phi of t is going to be A, B, cosine of omega t. So that's how we're going to change the angle by turning the handle. And let's get some more space right under here. Yeah, so what's next? Faraday's law. So E is equal to minus d phi dt. You have a minus, then we're going to get another minus sign, minus AB omega sine omega t. So this is our alternating voltage. Let's pull the omega out front, so that's frequency. We've got A times B is just the maximum flux, sine of omega t. So you'll see a couple of things. We're going to, first of all, here's our voltage, T, E, it's sinusoidal, so it alternates. And in fact, the amplitude is proportional to how fast we turn it. Okay, So we'll get a higher voltage with a higher frequency. Now, we can also get higher voltage with more turns. So the formula that you're going to be using in your homework, if the coil has n turns, then you just multiply this by n. So each turn of a coil here, gives you that much more flux. So we'll just end up with E is equal to omega n AB sine of omega t. So right there we have our generator. When we get to alternating current circuits next week, we'll learn about power and voltage, power and resistance and things like that. But right there, this is our alternating voltage generator. So we hook it up to a circuit, then we'll get currents and Ohm's law, which will be interestingly somewhat modified. But we're actually going to retain all of our, or some of our basic formulas. So this is an alternating voltage generator. So that's the first thing. With the alternating voltage, we're going to be able to have circuits that make charges oscillate back and forth. Charges oscillate back and forth. They're accelerating. We're going to get electromagnetic waves. Okay, but we still have a bit to do. Check the clock again. Okay, good. So I'll assign a couple homework problems on this topic here. And we now have one more important topic out of chapter, what is it, 28? The self-inductance. And this is also an application of Faraday's law. So our next topic is self-inductance. And I'll tell you what that is. Self-inductance. What we're going to do is just imagine having a power source, battery, and here's a circuit. We've got a switch. We're going to do a short circuit, but let's just say there's enough resistance in here not to burn things up right away. Okay, so there's some resistance in the circuit. We're not going to specify it at the moment. So we close the switch. I'll just draw that. So close the switch, and current begins to flow. For example, we've done this before with a capacitor in there, and the capacitor charges up, right? Current begins to flow. Yeah, for that matter, I could actually put a capacitor in here, and a resistor for that matter. Let's just put the whole thing in there. We'll put a resistor in here, and a capacitor. But we've already solved that RC circuit. What we're now after, though, is another subtlety that's in here, namely the following. Current begins to flow, and this current generates its own B field because these are straight wires. So we're getting, as the current begins to flow, and until it stops flowing, we're getting a B field here. And by the right-hand rule, getting a little X here on this side, and B field out on this side. Okay. So what's happening here is there is induced B field. But if there's induced B field, then Faraday's law says there's some voltage associated with that induced B field because it's a changing B field, right? Current begins the flow, induced B field, i.e. changing flux. There's changing flux in this circuit, okay, just by definition. And so there is, by Faraday's law, there's an EMF, and it's not this one here, minus dPV dt opposes, let's just give this one a 0, E0, opposes E0. And that happens for any circuit, and we refer to that as the self-inductance. Okay. So there's one more step I can take there. That's a self-induced EMF. So this is the self-induced EMF. And it opposes the battery supply there. Now, because the flux itself is proportional to the current, we can introduce a new circuit element. So continuing this argument, because phi sub B is going to be proportional to the current that's flowing, we can write this E here is equal to minus L di dt. In other words, we can introduce a new circuit element because this L will actually depend on the configuration here, how many turns and so forth. So that's how we can introduce a new circuit element and actually a new voltage that we're going to plug into Kirchhoff's laws. So yeah, let's characterize this L here. You'll see there are expressions for the inductance of, say, a coil with so and so many turns, but in principle, it's always for any closed circuit that, you know, encompasses an area. Okay. So yeah, I'm going to skip the inductance for a coil. You guys look that one up. Yeah. So let's go ahead and continue with this thing here. So we've got this piece of L is equal to minus L I dt. The circuit element, what are the units? Well, we know these are volts, and these are amperes per second. So volt seconds per ampere, and that is called the Henry. Right, we're all just using consistent units here. And do I have time to do a differential equation? So yeah, this is a, oh yeah, so the next thing is the circuit element. L looks like this, in honor of a coil with so and so many turns. Okay. And if we had our idealized circuit there, we would now, I could, you know, say my battery was E0, and then I'll leave the switch out, there's L, and then I could have had C, L, and R. So it's our goal to be able to talk about the behavior of a circuit like this. But yeah, this is the one where we're just taking into account that. And you know, we can build in circuit elements that control the amount of inductance, okay, as opposed to just the random amount that was here in principle. So yeah, what I want to do next is a circuit, not this one, a simpler one. And I need a few minutes for that. Well, let's go ahead and set it up. So next, we're going to do the RL circuit. And the idea is we're going to have, say, a battery. I can drop the 0 there. You know, that can get confusing, but yeah, E. We're going to have a battery and we're going to close a switch, and so I'll draw my switch in here. At time t equals 0, we'll close the switch and see what happens. Okay. And this is the inductor L. There's a resistor R. We close the switch and current flows. And actually current's going to continue to flow, but we're going to have this circuit element in there. So what I'm going to do is just set up Kirchhoff's law for this thing. Yeah, so since we've talked about waves, we're definitely in the part of the subject where we have to do time-dependent behavior of circuits. It's no longer just a simple Ohm's law, but rather it's going to start up and current's going to flow. So Kirchhoff, that's the way to look at these things. We'll start at the bottom left corner. We have E, then we're going to have minus L di dt. Minus IR is equal to 0. And this we have to integrate. Good. I'm gonna set this up. We're not gonna finish the integration today. So what we want to do is find I of t. There's another thing we can do, is we can multiply this equation by I, multiply star by I, and what do we get? We get EI minus LI di dt minus I squared R is equal to 0. And I'll actually write it this way. We'll bring this over to the right side. Li di dt plus I squared R. We're going to end with this. We haven't even solved this equation yet, which we're going to do, differential equation. But we can analyze this thing. So we'll start the next hour with this. Let me just show you what we have here. This is power. Okay. This is power being used by this entire circuit, okay, because it's the power being supplied by the battery, okay. I delta V, right, IE, that's the voltage, times the current. It has two parts. I squared R is clearly the power being dissipated by the resistor. Okay, power dissipated by the resistor. And this expression is really interesting because that's the power that's being, or that's the power that's going to the inductor. And what's going to happen is di dt is eventually going to come to a stop. So di dt will vanish, and there will be a power integrated over time, which will be the amount of energy stored in the inductor. So we're going to learn about energy stored in a magnetic field. We already had energy stored in an electric field. So yeah, the next topic, because it'll take a little longer than we have right now, is going to be to integrate this, find this is a function of time. We'll get the time-dependent behavior, and then we'll look at the amount of energy. This was just dissipated by the resistor. We'll look at the amount of energy stored in the magnetic field. Okay, I almost forgot. There is homework. And what is this? 25. Homework 25. Let's see what I have here on my list. So I have chapter 30. These are mostly easy. 22, 23, and then 42 and 44. So these are more wave stuff, and these are spectrum of electromagnetism stuff here. And then we go back to chapter 28, and I have two problems on generators, 45 and 46. Okay, moving right along. There you have it. Good. See you guys next time.